All right, let's jump right in. Today, we're tackling one of the biggest, most powerful ideas in all of math, the vector space. But look, forget all the dry, dusty textbook definitions. We're going to think about this in a totally different way, as the ultimate math playground.
So, to kick things off, here's a weird question for you. What in the world does a video game character and, say, a sound wave have in common? I mean, really. One is jumping around in a 3D world, the other is this complex audio thing. What's the connection?
Well, it turns out they both live in a world that has a very special set of rules. A world where you can add things together and scale them up or down. And it all works in a super consistent, predictable way. And that world, that's a vector space.
Okay, so to really get our heads around this, let's lean into that idea. Let's build out this vector playground and meet the players and see what kind of tools they're working with. So, just for a minute, try to forget about abstract math sets and all that. I want you to actually picture a playground. But this isn't for kids, right? This is a super special, carefully designed space where these mathematical objects we call vectors get to play and interact with each other.
And in this playground, you've got two main things to worry about. First, you have your vectors. These are the players. You can think of them as arrows pointing somewhere, or maybe a list of numbers, or even way more abstract things. Then, you've got your scalars. This is the toolbox. These are basically just regular old numbers that we use to mess with our players. You know, to stretch them, shrink them, or even flip them completely around.
You know, every playground has its rules, right? Things you can and can't do. Well, in our vector space playground, there are really only two main games you can play. Two basic actions that define, well, everything.
Okay, game number one is just combining players. It's called vector addition. All it means is, if you take two vectors that are already inside the playground and you add them together, the result has to land somewhere inside that same playground. It can't just magically end up outside the fence. This is a super important rule called closure, or as our source material calls it, internal composition.
And the second game? That involves using our toolbox. This is scalar multiplication. You grab a scalar, just a number, and you use it on one of our vector players to stretch it or shrink it or flip it. And just like before, the result has to stay inside the playground. This is what we call external composition. And that's the bottom line here. No matter what you do, adding or scaling, you can't escape the playground.
So we've got our players, our toolbox, and the two main games they can play. But for a playground to be an official, certified vector space, it has to follow a pretty strict rulebook. Let's take a look.
So why have this whole rulebook? What's the point? It's all about making things predictable. These rules, which are technically called axioms, they're a guarantee that no matter how you add or scale these vectors, the results are always consistent and well-behaved. It's what makes the math just work everywhere, for everything.
Let's start with the addition checklist. First up, you add two vectors, the result stays in the playboard. Check. Second, there has to be a special zero player, a vector that, when you add it to anything, doesn't change a thing. Got it. Third, every single player has to have an opposite, a twin, if you will, that when you add them together, they cancel each other out and get you back to that zero player. And finally, number 4, the order you add them in doesn't matter one bit. A plus B is always the same as B plus A. Then we have a few rules for our toolbox for scaling. First, just like with addition, when you scale a vector, it has to stay in the playground. Easy enough. Next, using the number 1 from your toolbox is basically a do-nothing move. It leaves the vector completely unchanged. And finally, the two games have to play nicely together. It doesn't matter if you add vectors first and then scale the result, or if you scale them individually and then add them up. You get the exact same answer either way.
Okay, now for the really fun part. We have all these rules, which means we can basically become detectives. We can look at any random collection of things and test it to see if it's a real, certified vector space or just a convincing fake.
Yeah, see, just because you can add some things together and multiply them by numbers doesn't automatically get you a golden ticket. It's not that easy. So let's look at a case straight from our source material that looks like it could be a vector space, but when we put it to the test, it totally fails. And this example just illustrates the failure perfectly. So imagine a playground where the main rule is this. For any vector, let's say it has 3 numbers, x, y, and z, those numbers have to add up to 0. Okay? So we grab two vectors that both follow this rule, their numbers add up to 0. But then we add those two vectors together. And the new vector we get, its numbers add up to -36. Well, -36 is not 0. This new vector has broken the rule. It has literally landed outside the playground fence. So verdict, failed. This is absolutely not a vector space.
You know, Dr. Gajendra Purohit in the video we're looking at gives another fantastic reason why something might fail the test. He points out that if you take rational numbers, but you only allow yourself to scale them with integers, that's not a vector space. And why not? Because the toolbox, the integers in this case, is incomplete. It's not what mathematicians call a field, because you can't always find a multiplicative inverse. Basically, if your toolbox is faulty, the whole playground gets disqualified. End of story.
Okay, so we've defined the playground, we've gone through the entire rule book, but you might be wondering, why do we care so much? Why are we so obsessed with this specific set of rules? Well, here's the magic part. Any system that follows this rule book unlocks a whole universe of powerful mathematical tools.
And believe me, these playgrounds are everywhere. The entire field of linear algebra, it's literally built on the idea of vector spaces. Computer graphics, moving characters around in a 3D world, that's all vector spaces. Physics, when you're describing forces and velocities, vector spaces. Data science, trying to make sense of these massive, complex data sets, you guessed it. And yeah, even that sound wave from our very first question can be represented as a vector in some massive, mind-bogglingly huge vector space.
And that, right there, is the ultimate power of this whole concept. A vector space gives us a universal language. If you can prove that something, and it can be anything from a financial model to a quantum state, if you can prove it behaves according to these simple rules, you suddenly get to inherit over a century's worth of powerful mathematical machinery for free. It's like unlocking this massive, pre-built toolkit that you already know is going to work on your problem, perfectly and predictably.
So, I'll leave you with this question to chew on. Now that you know the rules of the playground, you know you need addition, you need scaling, you need that special zero player, and all those other rules. What else out there in the world could actually be a vector? The answers might just surprise you.